Hello scientific brilliant people, how are you today? So today I'm going to discuss about the equations of motion in one dimension. There are three equations of motion that I'm going to derive, and these equations of motion are for one dimension and acceleration being constant. So I find this equations of motion to be very confusing among grade 9 and 11 students, so I decided to make a video upon the same. Here these three equations would be derived on the basis of a particular situation. So here is a velocity time graph given to you, and I'm going to describe the entire situation in reality over here. So like, what does this graph represent in reality, that I'm going to show it to you over here. But before this, please watch my lectures on motion in one dimension so that you can understand that what is slope. The slope of velocity time graph gives you acceleration, area gives you displacement, and straight line has constant slope. These are already the things which are described in the lectures before, and I'm going to, you can find those lectures links in the description over here. So slope is y2 minus y1 upon x2 minus x1. You require 2 points to find out the slope. So now let's start this topic. So here is a velocity time graph, and at time is equal to 0, the object had some velocity, say u, that is initial velocity. So at time is equal to 0, the object has got velocity, say u, and suppose at time is equal to t, the velocity is v. So let me show it to you over here, that at time is equal to t, the velocity is v. So these are my 2 points. This is point 1, this is point 2. We always write x coordinate first and then the y coordinate. So this point is TV, and this point x coordinate is 0, y coordinate is u. Now I'm going to call this as point 1. So point 1 is always x1 y1. So x1 is 0 and y1 is u, and let me call this as x2 y2, where x2 is t and y2 is v over here. Now v is the final velocity, u is initial velocity, now what does this graph represent? This graph says that as time passes, the velocity increases of a body. So at time is equal to 0, it at this velocity. Now as time increases, the velocity keeps on increasing. So let me take up a case that, say, at time is equal to 0, this is time is equal to 1 second, time is equal to 2 second, time is equal to 3 second. The speed keeps on increasing, or the velocity keeps on increasing, and the object is moving over here in a straight line path towards, say, east direction. So let's assume its speed is 5 meter per second, then 6 meter per second, 7 meter per second, and then 8 meter per second. So as you can see that after 1 second, the velocity increases by 1 meter per second. Again after 1 second, the velocity increases by 1 meter per second. Again after 1 second, the velocity increases by 1 meter per second. So over here, acceleration can be referred as 1 meter per second square. So had it been the case like from here to here, the velocity is increasing by 1, then here velocity is increasing by 2, then velocity is increasing by 3, then for that situation we cannot apply the following three equations. So here throughout the journey the acceleration is constant. This is what the graph represents. At time is equal to 0, this is 5 meter per second, and suppose this car ends its journey at 3 seconds, over there the velocity is 8 meter per second. So here the acceleration is constant and a body is moving in one dimension. So now let's try to apply these concepts over here, and I'm going to find out the slope of this particular graph. So slope is equal to y2 minus y1 upon x2 minus x1, and I know that the slope of velocity time graph is acceleration. because change in y-axis upon change in x-axis is what is called slope. So change in velocity upon change in time would be our acceleration. So slope is change in y-axis upon change in x-axis, that is y2 minus y1 upon x2 minus x1. Over here, change in y-axis is change in velocity upon change in x-axis is change in time, which is called acceleration. So I would be getting the acceleration. Now the 2 points which I am going to consider over here are the following. This is x1 y1 and this is x2 y2. So y2 minus y1, so y2 is v and y1 is u. So v minus u upon x2 minus x1, so x2 is t and x1 is 0, so here it would be t minus 0. So the acceleration itself is equal to v minus u by t, correct? Now I am going to cross multiply it, so I am going to get at is equal to v minus u, and from here v is equal to u plus at, because this minus u will go on that side, and I am going to get the relationship between final velocity, initial velocity, acceleration and the time of the journey. So guys, this is very important thing, and this is our first equation of motion that I have derived. Just by finding the slope, you will be able to find out the acceleration, and if you solve, you are going to get the relationship between final initial velocities, time taken and the acceleration. So now let's move on to the second part. So in the second part, I am going to find out the area under the graph, and this is my second equation I am going to get. So I am going to find out the area under the graph, and area is length multiplied by breadth. So y-axis multiplied by x-axis, so it would be velocity multiplied by time. So I would be getting the displacement. And area of what? So area under the graph, that is what we are going to find out. So this was our initial point, this was our final point. I am going to drop two perpendicular lines. Like this, and over here it is already drawn, and I'm going to find out this area, people, the area which is just below our graph with x-axis. As you can see that the shape is trapezium, and if you are unable to apply the area formula for trapezium, then you can divide this graph into two parts like this. So this is the area of the rectangular portion, and this is the area of the triangular portion. So you can find out the area of triangle and you can find out the area of rectangle, and you can add their areas to get the total area, and I would be getting the displacement. So as we had discussed that this point is time 0, this point is time t, this is u and this is v. So this length is u, so that means this length is also u, this point is v, so this distance is again v, because this point is v, this distance is u, this distance is v, so this full distance is v, so this distance is v minus u, so that this part is v minus u, correct? And this length is t minus 0, so this length is t. So if I divide this entire trapezium into two parts, one is rectangle and the another one is triangle. So and if I add that, I would be getting the total area, and the total area is the displacement, which I am denoting it by s. So area of the rectangle would be equal to length into breadth. So the length is u, breadth is t, so it is u multiplied by t, that is the area of the rectangle, plus area of the triangle is equal to half, base, which is t, the area of this triangle is half into base, so that is t, multiplied by the perpendicular height, that is v minus u, because this full height is v, this is u, so this is v minus u, right? Now I would just tell you from here that a is equal to v minus u upon t. So from here a is equal to v minus u by t. So if this a goes over here, so a multiplied by t is v minus u. So this value v minus u, that is at, I am going to substitute it over here. So this equation becomes s is equal to ut plus half, t remains the same. Instead of v minus u, I am going to write down at. So this equation turns out to be s is equal to ut plus half at square. So this is our second equation of motion, guys, very important. Now most of the videos, they don't talk about a very important point over here that I'm going to discuss. See, if you open up this complete expression, so this becomes s is equal to ut plus half vt minus half ut. So this is ut minus half ut is again half ut plus half vt, and again if I pull out half t common, then u plus v times t. Now this is v plus u by 2 times t, that is s. This is a very important equation that we apply in the numericals. So this is displacement, and this is what is called average velocity, and this is time. So this expression is average velocity, and average velocity is initial plus final by 2. But you can use only this equation when the acceleration is constant and the body is performing one dimension, because we are deriving everything with the help of this graph. Right, guys? An extremely helpful equation. So average velocity is equal to u plus v by 2, and the displacement is average velocity into time. You can use this, and you can use this in your expression as well. So now let's move on to the third equation. So our third equation of motion, so the previous equation of motion was s, that was equal to u plus v by 2 times t, and the first equation of motion was a is equal to v minus u by t. Correct. So I'm going to take t over here and a over here. So it is like at is equal to v minus u, and then t is equal to v minus u by a. So this is the equation that I'm going to use over here. So this time I'm going to substitute it over here. So I get s is equal to u plus v by 2 multiplied by v minus u by a. So guys, this is a mathematical identity. A plus b multiplied by a minus b is a square minus b square. So v plus u and v minus u, so this is v square minus u square upon 2a, that is s. Now if I cross multiply over here, so I get v square minus u square is equal to 2as, and this one is our third equation of motion. So guys, we have derived all the three equations of motion, and these equations are only to be applied when an object is moving in a straight line and acceleration is constant, because we have derived all these three equations by considering this graph. So if you are applying it to a circular motion, there are some exceptions, and I would like to tell you about the same. Suppose the body is moving in a circular path like this, correct, and the object was here. Now the object goes around a circular path, reaches over here, finally again reaches over here. This is not a one dimension motion. As you can see that over here the x coordinate is something, but the y coordinate is 0. But when this body reaches over here, it will have x and y coordinates both. So this is an example of two dimension motion. So you cannot apply this equation over here, but yes, this object has a shadow over here on x-axis, and this object has a shadow here on y-axis. Suppose you are shining a light like this, This is the light which is falling on this particle, so its shadow would be over here. And if one light you keep it over here, then its shadow would be falling over here. So if this particle is performing circular motion, the x-axis shadow would be always remaining in one dimension and y-axis shadow would be remaining in one dimension motion. Over there, for these individual shadows, you can apply the equations, but not for an object as a whole. So guys, hopefully you have enjoyed my explanation. Please subscribe my channel if you have not done so, and keep on writing good comments that can boost up my morale as well. Thank you for watching the video, guys.